Assalamu alaikum and good morning, everyone. So today we're going to start off with writing down the summary of all the complex ion and molecules that we have looked at for copper and cobalt. But before that, there is something that I want to correct on page 10 of your notes. Part B, where the first step of adding sodium hydroxide to form the copper hydroxide precipitate, that reaction is not classified as a ligand substitution reaction. So they don't see it as hydroxide kicking out water molecules, but rather hydroxide is acting as an acid, as a base. So it picks up hydrogen ions from two water molecules. So instead of calling this a partial ligand substitution, we can call it a precipitation or an acid-base reaction. So in this case, our hydroxide is acting as a base and our water molecule, water ligands are acting as our acid, okay? So as you can see, if I look at H2O only, which is the ligand, and hydroxide ion picks up this proton from the H2O, I will form OH minus plus H2O. Okay, it's not easy to see, but if I color code them, H2O after losing its proton becomes OH minus, whereas OH minus after picking up a proton, it becomes H2O. So more accurately, this process is not a ligand substitution, but rather an acid-base reaction. Likewise, for the reaction in the box below at the bottom of page 10, same thing. The ammonia is acting as a base here where it accepts the proton from the water molecules. So this is an acid-base reaction. They don't classify it as a ligand substitution. For cobalt, the same thing happens. On page 11, part A, where you are adding sodium hydroxide. So this is not considered a partial ligand substitution or not a ligand substitution. Hydroxide in this case is again acting as a base and it picks up a proton from, it picks up a H plus from H2O ligands in this complex, okay? So because we are producing precipitate in this case, we can call it a precipitation reaction or an acid-base reaction, okay? That's on page 11, part A. I wouldn't call that a ligand substitution reaction. And now we move on to the bottom of page 11, where we summarize all the complex ions that you are expected to know under this learning objective. Okay, so copper 2+ is actually copper with 6 water molecules, and it is in aqueous state. Copper 2+ appears as blue solution. When you add hydrochloric acid to your copper 2+, your blue solution will turn into a yellow solution of CuCl4 2 minus. Since it is a yellow, it is a solution, then it is in aqueous state. The formation of copper hydroxide is when you add a few drops of sodium hydroxide or a few drops of ammonia. So that's why when adding sodium hydroxide or ammonia, you get the same product, even though the starting material is different, because they are both bases. That's why they give you the same product, which is copper hydroxide. The nature would be a solid or a precipitate. It doesn't matter which one you want to write it, but usually if it's a precipitate, we write it as solid, and it has a pale blue color. And of course, when you dissolve this precipitate in excess ammonia, the precipitate will dissolve and the solution will turn into a deep blue or dark blue solution. And of course, it would be an aqueous. As for cobalt, cobalt 2+, cobalt sulfate, cobalt nitrate, and other cobalt complexes that is just made up of Cu2+, would have a pink solution as its appearance. And because it's a solution, then it is aqueous. If you add hydrochloric acid to your cobalt 2+ ions, it will turn into a blue solution. Now remember, when adding hydrochloric acid, 4 units of chlorides will remove or kick out all the 6 water molecules around the cobalt ion in the center. Because it's a blue solution, then the nature would be aqueous. Next is just by adding a few drops of sodium hydroxide or a few drops of aqueous ammonia, where acid-base reaction occurs here. It's not ligand exchange as mentioned to you in the previous lesson. So I've corrected in this lesson that when you add sodium hydroxide or ammonia to your cobalt 2+ ions, what happens is that an acid-base reaction will proceed. Okay, so cobalt with cobalt hydroxide is a precipitate, so we would expect to write it as a solid, and the color would be blue precipitate, something similar to your copper hydroxide. And lastly, the main difference is that if you add excess ammonia to your cobalt hydroxide ions, instead of having only 4 molecules of ammonia occupying the metal center ion, this time we've got 6 molecules of ammonia surrounding themselves around the cobalt center. So this is an example of a wholly ligand exchange or a whole ligand exchange. The appearance of this complex, cobalt with 6 ammonia molecule, is a brown solution. And of course, it is an aqueous state. So if you just remember this formula as well as their appearance, also to remember how you can get this formula. What I mean by that is CuCl4 2-, you can get this complex ion when you add hydrochloric acid to your copper 2+ ions, things like that. Okay, right, so this section is done for the ligand exchange. What I want to do next is to have a look at the questions before we move on, because you will notice that the exercise 28.1 is actually very thick, because I can confidently say that every single paper, okay, almost every single paper of your paper 4 will have a question on transition metal. So that's why the exercise, the questions in the exercise are also thick because these are actual exam pass year questions. Okay, so that's done for now, this section 5, which is ligand exchange. Now I would like to move on to exercise 28.1, and the first few questions may you may not have enough space, so please use a foolscap paper. Okay, so I'm just going to set this up while you prepare. Okay. Right, so I'll have one window showing the questions and the other window showing the answers. But how do I do that? But how to do that? Open a new window. Okay. Get out of there. Right, the first question that I want to look at would be question number 3. Okay, so question number 3. Please don't try to squeeze in everything in your question paper. As mentioned earlier, the first, I don't know, first few questions of this exercise does not have enough space for you to answer. So please use foolscap paper. Okay, question 3. Many commercial copper and brass polishes contain ammonia. The tarnish that forms on the surface of copper is often copper sulfide, CuS. In the presence of oxygen from the air, NH3 can combine with this copper sulfide to produce the soluble cuprammonium sulfate, CuNH34SO4. Okay. So you must remember in copper sulfate, it is made up of the copper 2+ ion, which is the same as having 6 water molecule arranged around that copper ion. And then it is saying that NH3 can combine with this copper sulfide to produce this formula. Okay, CuNH34SO4. Same thing, it is made up of the sulfate ions, which is not what we're interested in, and the copper with 4 ammonia molecule. Now, let me remind you, this copper with 4 ammonia ligands is the same as copper with 4 ammonia ligands and 2 water molecules. So, sorry, it should be Cu2+. So it's just the way that they have written this formula down. They have omitted the other 2 water molecules that give this complex ion the octahedral geometry. Okay, right. So they want us to construct an equation for this reaction. So we want to show how the copper 2+ ion, which is the blue solution, changes to copper with 4 ammonia molecules. Now, if you remember from the previous table that we were just looking at, you should already automatically think about the color of the copper with 4 ammonia molecules, which is dark blue or deep blue. Okay, so this is dark blue solution, and water is like lighter blue solution. Okay, construct an equation for this reaction. Okay, so Oh, they actually want you to follow the reaction. Okay, so then you will just start with copper sulfate plus oxygen plus NH3, and you try to balance it to get copper with 4 molecules of ammonia, and the counter ion is the sulfate. So usually the counter ion, you have to spot quickly that we're only interested in the formula or the ion that contains the transition metal. Okay, so in this case, our sulfate is not that important. And apparently to balance this, I don't know if you were able to balance that quickly. We need 4 molecules of ammonia, since in the product you also have 4 molecules. And I believe oxygen needs to be balanced, which is 2O2. Okay, that's to answer question number 1, 3 part 1. To answer question question 3 part 2, state the color of the cuprammonium sulfate solution. So this cuprammonium sulfate solution is actually this cuprammonium sulfate. So the color, the sulfate is colorless, so technically it just follows the cation, and the cation is a copper with 4 ammonia molecules, which should appear as dark blue or deep blue solution. So that answers your question number 2, deep blue solution. And lastly, describe what you would see if a solution of the cuprammonium sulfate was diluted with water. So that means we add H2O to our complex ion with 4 ammonia ligands or ammonia molecules. So what happens is that it will go back to the original Cu with 6, because you're adding water. Okay, water will just reverse the process of transforming copper 2 plus to copper with 4 ammonia molecules. Okay, so the color change would be from dark blue to light blue. Done. Oh, explain. Okay. So they want us to explain. Well, the explanation is there. The copper with 4 ammonia molecule is now the ligands. The ammonia ligands is now replaced by water. Okay, so we can say that ammonia and H3 ligands have been replaced with water. Okay, next question, part D. How do I add a page? Okay, still on question 3, part D. When sulfuric acid is added to Cu2 plus, no color change occurs, but when concentrated hydrochloric acid, okay, so the hint there is hydrochloric acid. So again, Cu2 plus is actually your copper with 6 water molecules. Okay, you add hydrochloric acid, or more importantly, the chloride ions. And if you remember, chloride ions are much bigger. So only 4 chloride ions can accommodate around the center of the copper ion. Okay, so the solution turns yellow-green. And yes, we already know why. What species is responsible for that yellow-green? It would be the CuCl4 2-. The solution reverts to its original color when it is diluted with water. Okay, so if I just write down the balanced equation of this, okay, so if I kick out all the 6 water molecules so that I can have 4 chloride ligands to be arranged around the copper, obviously I have 6 water molecules that are being kicked out. I don't know if you still remember that this reaction is actually a reversible reaction. So this help us answer the last line of this first paragraph. The solution reverts to its original color. Okay, so first I will write down this to be blue solution or blue aqueous, it's fine. And then we've got the yellow solution, right? And then they say if you add water, so what happens is that if you add water, water goes up. The Le Chatelier's principle will favor the reverse reaction. So you are now producing more blue solution. Okay. So this time you go from blue to yellow, and then yellow solution back to the blue color. Okay. The question is asking, suggest the type of reaction occurring with HCl, suggest what is formed during the reaction, and write an equation for the change. So we will say, for part D, ligand exchange is happening. Okay, they also want you to write an equation for the change. Okay, so first you start with CuH2O6 2 plus 4 chloride ligands. So you kick out all the water molecules so that 4 chloride ligands can arrange themselves around the copper central ion plus 6H2O. Okay, and then of course you want equation could include HCl on the LHS, for example. Oh, okay. Okay, so we've already got the name of the reaction. We've already got suggest what is formed. So that's the copper chloride. Yeah. And write an equation for change. Yep. Okay, next question would be question 24. Oops, sorry. I think it's this one. Okay, question 4. When concentrated HCl is added to a solution of copper 2+, so that means we are adding copper with 6 water molecules, 2+, plus HCl. So that means you expect the chloride ions. The solution turns yellow. Yes, confirm that that yellow solution is our CuCl4 2 minus. Okay, you start with a blue solution. And then they want you to state, the solution reverts to its original color when it is diluted with water. Okay, so if this was the balance equation of this reaction, and as we all know that only 4 chloride ligands can arrange themselves around the copper 2 plus center, that means all our water molecule has been kicked out. The solution reverts to its original color. I don't know if, let me just check if that equation is expected of you. Okay. What am I looking at? Oh gosh, I should be looking at question 4, sorry. Okay, so state the formula of the species responsible for the yellow color. That's the formula. And name the type of reaction that has occurred. So this is a ligand exchange. Okay, so that's part 1. Question 4B part 1. I hope that's okay and clear to you. I don't mean to make you confused. Okay, so question 4B. 2. Ammonia can react as a base or as a ligand. Describe the color changes that occurs when NH3 is gradually added with stirring to the yellow solution. So that means we are starting with the yellow solution. We add ammonia gradually. So that means if we add ammonia drop by drop, we will produce the copper hydroxide. H2O would be 4. And then in excess, drop in excess. So in excess is where your 4 ammonia comes in. And that makes your H2O becomes 2. Okay, so ammonia will kick out 2 of the hydroxide ions and 2 molecules of the water ligands. Okay, now it mentions that there are 3 ions or compounds responsible for the new color. Okay, so this is not a new color, that's considered old color. So I've only got this copper hydroxide, which is a blue precipitate, and copper with 4 ammonium, which is a dark blue solution. So that leaves me with, where's the other one? Which species are we talking about? Okay, so what did I want to do today? Oh, this is a deep dark blue solution, whereas the copper hydroxide would be blue PPT. Okay, so far, as I mentioned, you've only got 1, 2. The third color is actually copper chloride going in the reverse direction to reform the Cu2 plus ion. Okay, so that's why it's like, I know you're adding ammonia, but ammonia is aqueous. Aqueous contains water. So it's just the same effect like adding water to your copper with 4 chloride ligands. Okay, so because you are reverting the color of the CuCl4 to its original starting material, starting color, then it should have an appearance of blue solution. Okay, so these are the 3 colors that you have to fill in. 1, blue solution, blue precipitate, and deep dark blue solution. Okay, what is the question asking? Identify the 3 ions or compounds responsible for the new colors. Okay, so you will see that you can start with the solution will go from yellow to blue color due to the addition of aqueous ammonia. Okay, due to addition of aqueous ammonia. Okay, so the water in the aqueous will push the equilibrium back to the original starting of copper 2 plus, and then the blue precipitate is your copper hydroxide, whether you want to write down CuOH2 or CuOH2 and 4H2O, that's fine. And then in excess, this precipitate dissolve to leave with a deep dark blue solution. Okay, which is copper with 4 NH3 molecules and 2 H2O molecules. Okay, so that's question number 4. Next question that I want to look at is a little bit further away, which is question 35. Okay. So question 35, I think for question 35, I can answer it on the paper itself. Samples of cobalt. So we're now looking at cobalt, and cobalt with 6 water molecules is a pink solution. Are reacted separately with aqueous sodium hydroxide and an excess aqueous ammonia. Give the following information about these reactions. What happens if we add sodium hydroxide to the cobalt? We will produce a precipitate. This is a precipitation reaction. And the color of that precipitate is, I believe, the same, which is blue in color. Let me just check so that I don't make that mistake. Okay. Right. So the color would be a blue precipitate or blue solid. The state is just writing down whether it's a solid, liquid, or gas, or precipitate. Write down the ionic equation. Okay, so the ionic equation of, so I'll just here. Was it here? No, it's the other one. Sorry about that. Okay. Oh, let's go back. So to balance the equation, 35. Oh, no, that's 25. Let's see from here. That's 38. It's this one, okay? We should be looking at this. Okay. Right, the precipitate is a pale blue precipitate. Sorry, it's just a blue precipitate, not pale blue. You can write it as solid as well, blue precipitate. The ionic equation is actually the equation of the acid-base reaction. This is not 2+. Okay, so again, the rule is that only 2 hydroxide ions will replace the 2 water molecules. Well, actually, it's not, strictly speaking, it's not replacement, because if we don't consider them as ligand exchange, we consider them as an acid-base reaction. So only 2 hydroxide ions will sort of react with the water molecules. So you will form cobalt hydroxide, and this complex has a coordination number of 6. So that means the rest of the molecules or ligands is just water. Cobalt 2+. The type of reaction, so this is where the problem comes in. The type of reaction, they only accept precipitation or acid base. They do not accept ligand exchange. Okay. And the reaction of cobalt with an excess of aqueous ammonia, color and state the cobalt containing species. Okay, so when you add ammonia, this time I will write down the equation first because it's easier. Unlike copper, 6 ammonia molecules can be incorporated into the central ion. So that means I need 6 ammonia. All 6 are being kicked out. So all 6 water molecules are being kicked out. So 6H2O. Okay. The color and the state, the color of this cobalt was, we were just looking at it just now, cobalt with 6 ammonia molecules would be it would be brown solution. Okay, so brown solution. The state is in the solution, whether it's a solution or precipitate. Okay, and type of reaction, then this one we can say ligand exchange. Okay, next one, when concentrated hydrochloric acid is added to a solution of cobalt 2+, a blue solution of cobalt chloride is being produced or being formed, and the following equilibrium is established. So I'll just label this. This is a pink solution of cobalt 2+, and this is a blue solution of cobalt chloride. So the color is different for copper with 4 chloride ligands. The color would be yellow, but for cobalt it will be blue. But the number of chloride ions that sits around the metal center is the same, 4. Okay, so 4 out of 6 water molecules in cobalt 2+ will be replaced by 4 units of chloride ions. Use the Chatillon's principle to suggest the expected observation. So we need to write down the observation. When silver nitrate, Ag plus NO3 minus, is added dropwise to the blue solution of COCl42 minus. Okay, so we now have a blue solution and we're adding silver nitrate. There's no silver in this equation. There's also no nitrate in this equation, but because silver nitrate is aqueous or water, we know that the reaction will be shifted to the left. Okay, so the reverse reaction will happen. Another thing is, although not directly appear on the balance equation, we know that silver will react with chloride ion. So silver ion reacts with chloride ion to give silver chloride, which appears to be white precipitate. Okay, so you would expect white precipitate to form. Okay, now since silver reacts with chloride, the amount of chloride decreases. Okay, so that means concentration of chloride decreases. Le Chatelier's favor reverse reaction. Okay, so now COCl4 2 minus will go back to CO2 plus. So that means blue solution will turn pink. Okay, so the blue solution is COCl4 2 minus, and the pink solution is COH2O6 2 plus. Okay, so that is all for today. This is the kind of questions that they can ask you relating to ligand exchange. It's, as I said, they will ask you to identify the formula that causes this color, or they can ask you to write down the balance equation, identify what type of reaction. So this the kind of questions they can ask you is, you know, it can be anything. All right, so that's why you have to really learn and memorize these colors and the reagents that you need to add in order to get this particular complex. Okay, whether it's a complex ion or it's a complex molecule. Okay, so once you have done this, all right, I think right, as attendants, I will want you to fill in the questions and the forms. Okay, so please make sure you submit your forms by 4:30 today. Exception to those attending your mom. I think they will be busy the whole day, if I'm not mistaken. So they're excused to hand in late, right? But everyone else should be able to do this, complete the question, because I've literally already gone through them with you. Okay, Assalamu alaikum, and thank you, everyone.